Good morning, everyone. Thank you for tuning to my presentation. My name is Rafael Rodriguez, and today I'm going to quickly introduce you to the modeling of strength of materials. In particular, I'm going to talk about the yield strength and Vickers Hardness modeling of Haynes 282. Let's get started. The major source of power generation in the world continues to be coal power plants. In order to increase their efficiency, as well as to drastically reduce their environmental contamination, their operating temperature and pressure must be increased above 700 degrees C and 30 megapascals. However, the materials that are currently in use for the hot section of this plant cannot support these extreme conditions, so new materials that can must be designed. Haynes 282 is precisely a nickel-based superalloy that has been developed to address this need. By tuning the chemistry of this alloy as well as its post-heat treatment, the microstructure of Haynes 282 is designed to be made of an FCC ductile gamma matrix incredibly strengthened by the hard spherical nano-sized gamma prime precipitates with blocky chromium and moly-based carbides inhibiting grain boundary sliding. This microstructure then provides with outstanding mechanical properties, such as high yield strength at both room and high temperature, as you can see from the table listed in here. My work, however, consists of using computational tools to model this microstructure and further predict the strength of this material, to help in that way reduce expensive testing operations and inform future optimization designs. As you can see from the figure to your right, using a CALFAT software, I'm able to predict the fraction of the different possible phases of a Haynes 282 alloy as a function of temperature. With this information, and borrowing from the experience of basic physical metallurgy principles, I have set up a modeling framework that allows to predict the yield strength and Vickers hardness of Haynes 282. Considering the basic four classical strengthening mechanisms, I try to capture, first, the intrinsic strength of the material, which arises from the Peirce-Navarro stress of nickel matrix as well as the dislocation strengthening inherited from the casting process. Second, the grain boundary strengthening associated with the size of the grains. Third, the influence of the dissolved elements which provide soil solution strengthening of the FCC matrix. And fourth, the hardening influence that the volume percentage and size of the hard gamma prime precipitate has. By combining all these contributions, then an accurate yield strength value can be obtained. Furthermore, due to the lack of defining physics when it comes to modeling hardness and building upon the long-lasting steel tradition of correlated hardness and yield strength by a constant value, Vickers hardness can be estimated based on the obtained yield strength. To model the intrinsic strength of a material, the Peirce-Navarro stress of polycrystalline nickel as well as the Taylor formula to capture the influence of these locations are readily available. For the grain boundary strengthening, the classical high-pitch model is used with a literature survey tuned kappa coefficients. All these relevant numbers are listed here in this slide. The solid solution strengthening is modeled by the Giffen-Dirichlet nickel-based multi-component equation, where the calibrated element coefficients are listed here. Finally, the precipitation strengthening is modeled by the improved weak-strong dislocation precipitate pair couple model proposed by Galindo Nava a few years ago. Superimposing all these four contributions and estimating a data-driven hardness yield strength coefficient derived from literature information, we can test our model versus literature reported values. Taking as an example two of the most relevant recent publications on regularly cast and post-heat treated Haynes 282, the model prediction versus the actual measured and reported yield strength for a total of 6 different samples are comparing these figures. From the plots, we can observe that the model performs substantially well with a net average error in the order of 3%. Moreover, with this modeling approach, we can easily see the predominantly role that precipitation strengthening has in this alloy, since it alone provides more than half of the total strength this material possesses. Finally, using a data-driven hardness strength coefficient of 2.11, the hardness prediction performance can be observed in these figures. With an average error of 6%, we consider these predictions within the reasonable margin of accuracy for a Vickers hardness test. Based on these results, we can conclude that an effective yield strength and Vickers hardness modeling framework has been successfully designed by combining CALFA microstructure prediction as well as the sound strengthening models available in literature. The immediate next steps for enhancing this model are: first, to continue to collect more data and studies to better calibrate the model itself. Second, to incorporate new physics-based models that help predict the high temperature strength and hardness. And third, to tune the model so they can be implemented on additively manufactured Haynes 282 and other nickel superalloys. Thank you for your attention in this quick 5 minutes long presentation. If you have any questions or want more information about the details of my current work, feel free to email me at this address and I will be happy to get in touch with you. Until then, thank you and have a great rest of your day.